Hi everyone, in this video we'll be solving paper 2 variant 2 October-November 2024 AS level chemistry. Question 1. Vanadium, niobium and tantalum are metals in the same group of the periodic table. The shorthand electronic configuration of vanadium in the ground state is that of argon followed by 3d3 and 4s2. State what's meant by the term ground state. Ground state is the lowest energy state when referring to electrons. It's how you usually find electrons in an atom. Part 2. Show the electronic configuration of vanadium using electrons in box notation. The electronic configuration of vanadium is that of argon, which has 18 electrons followed by 3d3 4s2. Here you need to know how to fill up orbitals, right? So there are 5 orbitals in the d subshell and you've got 3 electrons for these 5 orbitals. Each electron fills up a separate orbital before they have to pair up. Since you only have 3 electrons, you don't need to pair up since you have plenty, more than enough orbitals to place these electrons. And then you have the 4s orbital where you have 2 electrons, so they are going to pair up with opposite spin pair due to the repulsion between them. Reduce the total number of electrons in the p subshells of vanadium atom. Here you need to know the electronic configuration of vanadium atom so you can add up the electrons in all of the p orbitals. So remember, you have subshells in all of the shells of electrons in the shells of an atom, and as the number of shell increases from 1, 2, 3 in the chronological order, the number of subshells also increases. So for instance, energy level or shell 1 only has s orbital, whereas shell 2 has subshells s and p. Shell 3 has s, p and d orbitals. 4 has s, p, d and f orbitals. This continues to increase. You also need to know the number of orbitals in each subshell. Subshell s has 1 orbital. Subshell p has 3 orbitals. Subshell d has 5 orbitals. As you can see right here, subshell f has 7 orbitals. Since each orbital can carry 2 electrons, that means shell 1 can carry 2 electrons. Then subshell p with 3 orbitals can carry a total of 6 electrons. Subshell d with 5 orbitals can carry 10 electrons, and subshell f with 7 orbitals can carry a total of 14 electrons. And the way that you fill up these subshells or write the electronic configuration is, we always start with the subshell that is closer to the nucleus or lowest in energy. That would be 1s2. Okay, so now we have to expand the argon configuration so we can find out the total number of electrons in subshell p, right? So we need to find out how all of these 18 electrons are occupied. Starting off with 2 electrons in the 1s orbital, then you move on to the next orbital, which is 2s2. That's followed by 2p6, which makes up 10 electrons. Then the next orbital closer to energy would be 3s2, that's 12 electrons. Now you're left with 6 electrons, which will be occupied by the 3p orbital. And as you can see, you've got 6 plus 6, that's a total of 12 electrons in the p subshell of vanadium atom. You don't need to write the electronic configuration, that was just for explanation purpose. Pelopium was the suggested name for a new element discovered in a mineral. It was later found to be a mixture of niobium and tantalum. Only one naturally occurring isotope exists. For each of niobium and tantalum, you're supposed to complete table 1.1 by providing the number of protons as well as the number of neutrons. The number of protons is the atomic number, so that's the lower number, or the number smaller in size. Just 41 for niobium and 73 for tantalum. The number of protons is the atomic number subtracted from the mass number, which for niobium is 93 minus 41, which leaves you with 41, and for tantalum that's 181 minus 73, which is 108. Define relative isotopic mass. This is one more definition that you need to know by heart. It's the mass of an isotope on a scale where carbon 12 atom has a mass of exactly 12 units. Part 3. A sample of fallopian contains 90.9% biomass of niobium and 9.1% of tantalum. Calculate the theoretical isotopic mass of fallopian based on these data, and table 1.1. Give your answer to 2 decimal places. Show your working. The relative atomic mass is equal to the sum of the product of percentage composition of each isotope and its atomic mass divided by 100. So that means the percentage composition of niobium multiplied by its isotopic mass, which is given in the table as 92.91, plus the percentage composition of tantalum, that's 9.1%, multiplied by its isotopic mass, which is 180.95, divided by 100. That leaves you with 100.92, correct to 2 decimal places. Question 2. Oxygen is a group 16 element. Write equations for the following reactions between sodium and oxygen. Sodium has a charge of +1 when it forms the sodium oxide compound, and oxygen has a charge of -2. That means you need 2 sodium ions to neutralize the charge of 1 oxide ion. So the chemical formula here would be Na2O. Since you have 2 oxygen atoms on the left hand side of the equation, you need to balance that, which leaves you with 4 sodium atoms on the right hand side of equation. That means you'll have 4 sodium atoms on the left side as well. The equation for the reaction between sulfur and oxygen, that would simply lead to the formation of sulfur dioxide. Draw a dot and cross diagram to show the species present in aluminium oxide. Draw outer electrons only. Alright, aluminium being a group 3 metallic element will donate the 3 electrons in its outer shell, and oxygen being a group 6 non-metallic element needs 2 electrons to complete its outer shell, which it will gain from aluminium to gain a charge of -2, whereas aluminium becomes a cation with a charge of +3 after losing all 3 electrons. Now what happens is, 1 aluminium atom loses 3 electrons, and 2 aluminium atoms are capable of donating 6 electrons. 1 oxygen atom can accept 2 electrons, and 3 of those would accept all of the 6 electrons donated by the two aluminum atoms. Therefore, you have the chemical formula Al2O3. As for their dot and cross diagram, aluminium will have lost all of the electrons in its outer shell, having gained a charge of +3, whereas oxygen will gain 2 electrons from aluminium to complete its octet and gain a charge of -2. Part 3. The maximum oxidation state of period 3 elements and their oxide varies across the period. State and explain the variation. Alright, here you need to know the formulae of all the oxides of period 3 elements, especially sulfur trioxide, because the oxidation state of sulfur dioxide is +4, which is not the maximum oxidation state for an oxide of sulfur. Let's start listing down the elements first. Those would be elements of the period 3, right? They form sodium oxide, magnesium oxide, Al2O3, silicon oxide, P2O5, phosphorus oxide, and then sulfur trioxide. The oxidation state of sodium is +1, and this increases across the period because it depends on the number of electrons in the outermost shell of the period 3 elements that they can donate or use for chemical bonding, for sharing, to form the oxide with the maximum oxidation state. B. Water reacts with both inorganic and organic compounds. Complete table 2.1 to give details of the reactions of some period 3 oxides with the water. You're supposed to start by mentioning the period 3 oxide that reacts with water to form magnesium hydroxide. That's pretty easy. That would be magnesium oxide. It's one of the reactions that you are supposed to memorize. And the pH of a metallic hydroxide is basic in nature, so the value for your answer should be between 8 and 12. I'll go ahead and write 10. Phosphorus oxide reacts with water to produce phosphoric acid, and this is obviously a proton donor, which results in an acidic pH. Your answer should be towards the lower end of the pH scale. I'd write 2 for my answer here. Write an equation for the reaction of methyl cyanide with water in acidic conditions. Okay, methyl cyanide, the reaction with water in acidic conditions is an acidic hydrolysis, which will convert the nitrile group or the cyanide group into a carboxylic acid functional group. So you'd have CH3CO2H over here, and then the nitrogen from the nitrile group will be converted to ammonia. However, as you can see, this reaction takes place under acidic conditions. That means there's an excess of protons in the solution, and ammonia, being a basic compound, will accept that proton to become ammonium ion. Now let's see if we have the elements balanced on both sides of the equation. Okay, so we've got 2 carbon atoms, and how many hydrogens do we have? 3 and 3, 6, right? So it's 3, 4 plus 4. We've got 8 hydrogen atoms here. Also, we have 2 oxygen atoms on the right side. That means we need to have 2 water molecules to balance this equation. And now we have 8 hydrogen atoms as well. And all other elements are also balanced. Draw the structures of the 2 alcohols formed during the reaction shown in equation 1. So equation 1 is the reaction between propene with water to form propanol. This is an addition reaction which converts a compound with double bonds into a compound with all single bonds. And you're supposed to show the reaction, show the structures of the two alcohols formed in this reaction. Now, this alcohol with all single bonds will exhibit one of the two forms of isomerism that we'll learn about. Those are structural isomerism or stereoisomerism. Stereoisomerism only occurs in compounds that have a double bond. Since this compound does not have carbon-carbon double bonds or just a double bond in general, that means it will not exhibit stereoisomerism. So we know that it has to form structural isomers. Structural isomers can form due to difference in the position of a functional group, which in this case is the hydroxyl group, or the structural isomerism can occur due to forming of branches in a compound. Since this is only a 3-carbon compound, no matter which way you write it, it would form the same branched structure. So the structural isomerism here would be due to the position of hydroxyl group. It can be either on the first carbon atom or on the second carbon atom, which would form propan 1-ol or propan 2-ol. Also, it doesn't matter whether you place the hydroxyl group on this carbon atom or this carbon atom over here, since both of them are terminal and there are only 3 carbon atoms. Since both of them are terminal carbon atoms, it would still form propan 1-ol. Right. So we've got propan 1-ol and propan 2-ol as our structural isomers. It's CH3, CHOH. Remember to put the hydroxyl group in brackets since it's a branch in the middle of the compound. This one's propan 1-ol and propan 2-ol. Part 4. Explain why alcohols are less acidic than water. Acidity of a compound depends on its attraction for protons when it dissociates in an aqueous solution. If a compound after dissociation in water has a very strong attraction for the protons or hydrogen ions, that makes it less acidic. However, let's look at the dissociation. Let's look at the dissociation of an alcohol. It undergoes dissociation to form alkoxide ion along with protons. Now, this equilibrium, you need to know here, this equilibrium lies to the left side. That means there are very few protons in a solution of an alcohol compared to the dissociation of water, where it forms hydroxide ions and protons. And that's because the alkoxide ion has alkyl group, which has a positive inductive effect because it pushes electrons towards the oxygen atom in the alkoxide ion, which increases the electron density on this oxygen. Since now, due to this increase in electron density, the alkoxide ion has a stronger attraction for the proton, which makes it far more likely to combine, which makes it far more likely for this alkoxide ion to combine with proton and shift the equilibrium to the left hand side than stay as an alkoxide ion. So once again, the alkyl group has a positive inductive effect. It pushes electrons towards the oxygen atom, making it far more likely for the alkoxide ion to combine with the proton and for the equilibrium to shift back to the left hand side, compared to water, which does not have an electron donating group like the methyl or the alkyl or an alkyl group. That means it is far more likely to dissociate and produce protons. Remember that acids are proton donors, whereas bases are proton acceptors. The stronger the ability of a compound to donate protons, the stronger is its acidic nature. And alcohols have a very weak ability to dissociate and produce protons. That makes them less acidic than water. See figure 2.1 shows the boiling points of water and other group 16 hydrides. Part 1, explain the trend in boiling points of group 16 hydrides from sulfur hydride to tellurium hydride. Alright, let's start with the factor that determines the boiling point of group 16 hydrides. The boiling point of these compounds depends on the intermolecular forces found in them. That means the forces of attraction found between, let's say, two molecules of hydrogen sulfide. We learn about three main intermolecular forces. Those are hydrogen bonds, permanent dipole forces, as well as London dispersion forces, which are also known as instantaneous dipole induced dipole forces. Hydrogen bonds only exist between molecules that have a hydrogen atom bonded to either oxygen, nitrogen, or fluorine. Out of these compounds, only water has hydrogen bonding involved in it. This is the strongest form of intermolecular force. Permanent dipole forces are found between polar molecules, that is, molecules that have elements with a large difference in their electronegativities. All of these group 16 hydrides also have permanent dipole forces between them. Last but not least, London dispersion forces or instantaneous dipole induced dipole forces are found between molecules of all covalent compounds, and this results from the electron cloud that surrounds an atom in all of these molecules. It depends on the number of electrons in a compound. So the greater the number of electrons, the stronger the strength of London dispersion forces between molecules. Now remember that London dispersion forces are found in all between the molecules of all covalent compounds, whereas permanent dipole forces are only found between polar molecules, and hydrogen bonds, the strongest of all, are only found between molecules where a hydrogen atom is bonded to oxygen, nitrogen, and fluorine. That means in water, the most significant intermolecular force is hydrogen bonds, whereas in the remaining hydrides you've got not only permanent dipole forces but also London dispersion forces. You're supposed to explain the trend in boiling points from sulfur hydride to tellurium hydride, and as you can see there is an increase in the boiling point. Now remember how I said the strength of London dispersion forces depends on the number of electrons found in the molecule of a particular compound. As the number of electrons increases, their strength also increases. And even though these hydrides have permanent dipole forces, they are not as significant when compared when considering the increasing strength of the increasing value of their boiling point. The Increase in boiling point occurs due to the increasing strength of the London dispersion forces between the molecules of group 16 hydrides due to the increasing number of electrons found in these compounds. And when the intermolecular forces between the molecules increases, that means a greater amount of energy is required to break these bonds or overcome these forces. In other words, a higher temperature is required to boil a certain compound. Explain why the boiling point of water is much higher than that of sulfur hydride. Once again, the molecules of water involve hydrogen bonding, whereas the other hydrides do not. And hydrogen bonding is the strongest intermolecular force of attraction. Question 3. Nitrogen and phosphorus are elements in group 15 of the periodic table. A. Nitrogen is found in inorganic compounds such as nitrogen oxides, nitrates, and nitric acid. Identify one natural and one man-made occurrence of nitrogen oxides in the atmosphere. Natural source of production of nitrogen oxides is lightning, and the man-made source is from internal combustion of engines. Write an equation to describe the role of nitrogen dioxide in the direct formation of acid rain. Here you can write one of two possible equations. I like to write the reaction of nitrogen oxide with water to form two different products, where you've got two nitrogen atoms on the right hand side, so you need to balance that equation, and that's it. Peroxyacetyl nitrate is a compound of a photochemical smog. Describe how PAN forms from nitrogen dioxide. This topic's been recently added to the syllabus, and you are expected to know that volatile organic compounds, abbreviated as VOCs, are also a pollutant in exhaust fumes. They are unburned hydrocarbons that react with nitrogen oxides in the air to form PAN. So that's how PAN forms from nitrogen dioxide. It reacts with volatile organic compounds to form these compounds. Part 4. Nitric acid reacts with basic oxides to form nitrates. Write an equation for the reaction of nitric acid with calcium oxide. This will produce calcium nitrate salt. Now, calcium has a +2 charge, whereas the nitrate ion has a charge of -1. That means you need two nitrate ions, to balance the +2 charge of calcium ion and form a neutral unit. This also results in the production of water. You need to balance the number of nitrogen on both sides. You've got 2 here, that means you'll need 2 on the left hand side as well. And by this method, all other atoms are balanced as well. Describe what's seen when solid calcium nitrate is heated strongly. When it's heated strongly, calcium nitrate undergoes thermal decomposition, which results in the production of nitrogen dioxide gas, and that causes the appearance of brown fumes. The equation for this reaction would be calcium nitrate getting decomposed to form calcium oxide, nitrogen dioxide, and oxygen. You'll have 4 molecules of the gas 2 molecules of the new salt or calcium oxide, as well as 2 of the reactants. You don't need to write the equation for this reaction. A common test for nitrates is a reaction with sodium hydroxide and aluminium. Equation 1 shows the reaction, and you're supposed to start with deducing the oxidation state of nitrogen in the nitrate ion. Okay. When you want to find the oxidation state of an element, you denote its oxidation state by an unknown variable. To that, you will add the oxidation state of the element that you are aware of. Oxygen in a compound has an oxidation state of -2. Since you have 3 oxygen atoms, you'd multiply that by 3, and this is equal to the total charge on this ion, which is -1, right? So that's x minus 6 is equal to -1. Shifting -6 to that side, you would have 6 minus 1. You would have 6 minus 1, that's plus 5. So the oxidation state of nitrogen in this ion is plus 5. Identify the species that's oxidized in equation 1. Alright, so the answer to part 1 is almost a hint for you to use the oxidation states of all the species involved in this reaction to write the answer to this question. There are a few elements that have their standard oxidation states. In here, that would be oxygen and hydrogen. Oxygen will always have the oxidation state of -2, and hydrogen will always have the oxidation state of +1 in a compound. That leaves you with nitrogen and aluminium being the elements that will change their oxidation states. We already know the oxidation state of nitrogen here is +5. Aluminium in its neutral element form, as any other element, would have an oxidation state of 0. And after the reaction, you are supposed to compare the oxidation states of the two elements. Once again, to find the oxidation state of nitrogen here, you would denote that by an unknown variable. Add to that the oxidation state of hydrogen, which is +1. Multiply that by the number of hydrogen ions, that would be 3, and the total charge of this compound is 0. That means the oxidation state of nitrogen here is equal to -3. As you can see, this is a decrease in oxidation state for nitrogen from +5 to -3, resulting from a gain of 8 electrons. This is reduction. Just using this fact that nitrogen has been reduced, you can deduce that aluminium must have been oxidized to form the new ion. So that would be aluminium. And you can even confirm your answer by finding out the oxidation state of aluminium in this tetrahydroxoaluminate ion, right? We've got an aluminium ion with 4 hydroxyl ions, and this sums up to a charge of -1. The unknown ion of aluminium denoted by X, to that you will add the charge of 4 hydroxyl ions. Each hydroxyl ion has a charge of -1. You have 4 of them, and their sum should be equal to this charge over here, which is -1. So X minus 4 is -1. That leaves you with +3. As you can see, this is an increase from the oxidation state of 0, right? So this is clearly oxidation. Ammonia is a basic gas. Describe how it's able to act as a base. Well, any base is a proton acceptor during its action as a base. 4 suggests the shape of the tetrahydroxyaluminate ion. Since it's got a central atom with 4 identical groups of atoms bonded to aluminium, this ion is tetrahedral in shape, or it has the tetrahedral geometry. And just in case you are curious about the bonding here, aluminium ion has a charge of +3, and each hydroxyl ion with a charge of -1 will form a dative bond with aluminium, and that's denoted by an arrow pointed towards the aluminium ion. As you can see, the 4 negative ions have a charge of -4, and since you only have +3 from the aluminium, this will result in the total charge of -1 for the entire ion. Figure 3.1 shows a sketch of some of the ionization energies of phosphorus. These ionization energies are known as successive ionization energies. Part 1. Construct an equation to represent the third ionization energy of phosphorus. First off, ionization energy is the energy required to remove an electron from 1 mole of gaseous atoms to form an ion. The first ionization energy is the energy that is required to remove the first electron from phosphorus and form the phosphorus ion with a positive charge. The second ionization energy will be the energy required to remove an electron from a phosphorus ion with a +1 charge. This will result in a phosphorus ion that has a +2 charge. And the third ionization energy will be the ionization energy required to remove an electron from this phosphorus ion with a +2 charge, which will result in a +3 charge. So that's your answer over here. Complete the graph in figure 3.1 to show the third to sixth ionization energies of phosphorus. Okay. What we'll see here in the graph is an increase in successive ionization energies of phosphorus. With each successive ionization energy, there is an electron is removed from a larger cation. As you can see, the first electron is removed from a neutral atom. The second electron is removed from a cation with a +1 charge. The third electron is removed from a cation with a +2 charge. And with each successive ionization energy, there is a stronger attraction for the electron and the ion because of this charge. With stronger attraction for the outermost electron, the successive ionization energies will increase generally, right? So you'll have a general upward trend in successive ionization energies of elements. In addition to this trend, there's also a large jump in ionization energy whenever an electron is removed from a shell that's closer to the nucleus compared to the previous electron. For example, let's put this into perspective using the example of phosphorus itself. Phosphorus, being a group 5 element, has 5 electrons in its outermost shell. And the sixth electron that's removed from a phosphorus atom would be removed from its second last shell. So as you can see, this second last shell is closer to the nucleus. That means there is a stronger attraction for the sixth electron compared to the fifth electron. As it's closer to the nucleus, so the nuclear attraction would be stronger. And due to this, you would observe the largest jump in ionization energy between the fifth and sixth values. So let's say if this was your sixth ionization energy, here you could denote the fifth one, fourth, and third. Complete table 3.1 to show the properties of nitrogen and phosphorus in their standard states. Nitrogen is a non-metallic element, so it has poor electrical conductivity and covalent bonding. Same is the case for phosphorus, and both of them have a simple structure. E, a form of solid nitrogen, has a lattice structure similar to solid iodine. Identify the type of lattice structure of solid nitrogen. That's simple molecular structure. All covalent compounds have a simple molecular structure except for those that we learn to have giant molecular structures like silica and diamond. F, at very high temperatures, phosphorus can form diphosphorus molecules which contain a triple bond. Describe the formation of the triple bond in terms of orbital overlap. Okay, so whenever you have single or double bonds, remember that the first bond is always formed by the overlap of sigma bonds, whereas the second and third, or all of the following bonds, are formed by overlap of pi orbitals. Sigma bond is formed using hybridized orbital. Since this is a triple bond, that means the phosphorus atoms would have sp orbitals or sp hybridized orbitals that overlap head on to form a sigma bond. And since there are two pi bonds, that means two unhybridized p orbitals overlap sideways to form two pi bonds. If there were four single bonds involved, like in the case of a methane molecule, then you would have had one s orbital combining with three p orbitals to form four sp3 orbitals. If you had a molecule with a double bond, for example ethene, then you would have had one s orbital combining with two p orbitals to form three sp2 hybridized orbitals. Whereas in a triple bond, only one s and one p orbital undergoes hybridization to form an sp orbital. Part 2. The bond energy of diphosphorus is 485 kilojoule per mole, whereas that of a nitrogen molecule is 944. Clearly, this is much larger than that of the diphosphorus molecule, meaning that the triple bond between nitrogen atoms is much stronger than the triple bond of phosphorus atoms. Compare the reactivity of diphosphorus and a nitrogen molecule and explain your answer. The reactivity would vary inversely with the bond energy. So the stronger the bond energy, the harder it is to break this bond and have the molecule involved in a reaction. That means a much higher amount of energy is required to break the bonds, the triple bond between nitrogen atoms. Therefore, the nitrogen molecule is much less reactive compared to the diphosphorus molecule. Question 4. Bromoalkanes are used widely in industry, although there's increasing concern about their environmental impact. Figure 4.1 shows a reaction scheme involving 1,2-dibromoethane. Part A asks you to complete figure 4.2 to show the mechanism for the formation of 1,2-dibromoethane. In reaction 1, include charges, dipoles, lone pairs of electrons, and curly arrows as appropriate. This is an electrophilic addition reaction since the carbon-carbon double bond is converted to a single bond by the addition of the electrophile here. To start off, let's explain what's happening over here. The electron density of the carbon-carbon double bond will cause a dipole formation in the bromine molecule. That is, it will repel the electrons in this bond away from the bromine that's closer to the double bond, right? So it will result in formation of partial charges. The bromine that's closer to the carbon-carbon double bond will gain a partial positive charge, and since the pair of electrons involved in this bond is now closer to the other bromine atom, it will gain a partial negative charge. Following this, the bromine, the single bond between two bromine atoms will break by heterolytic bond fission. That is, both of the electrons involved in this pair, in this covalent bond, will be gained by the bromine that has a partial negative charge. Now, there were initially two bonds between the carbon atoms. One of them will break down, and the electrons that were involved in this carbon atom, you need to understand that in each single bond, in each of the two bonds that previously existed between this carbon atom and this carbon atom over here, there was one electron contributed by both of these carbon atoms. Now that this bond breaks, one of these electrons will be donated to the bromine atom. So now the carbon atom donates an electron to the bromine atom. That means the other carbon atom which had provided this electron for the previous double bond is now short of one electron. That will give this carbon atom a positive charge, because the electron that it had contributed to the double bond has now been given to the bromine atom. And remember that the electron from heterolytic bond fission was gained by the bromine atom with a partial negative charge. So now it has a complete negative charge with an extra electron. This is attracted to the positive charge of the carbon, forms a bond by donating this extra electron, and this results in the production of 1,2-dibromoethane. For your answer, you need to know the partial positive and partial negative charge, as well as curly arrows where the head should represent the direction where electron is moving, and the tail should point at the location where the electron is coming from. B, the enthalpy change of reaction for reaction 1 is negative 90 kilojoule per mole. Where the enthalpy change of formation of ethene is provided, you are supposed to calculate the enthalpy change of formation of 1,2-dibromoethane. So the enthalpy change of a reaction is equal to enthalpy change of formation of the products minus that of the reactants. We are given with this value already. You need to find the formation of the product, here unknown, minus the formation of the reactant, right? Enthalpy change of formation of the reactant. So that's equal to 52.2 minus 90, and your final answer would be negative 37.8 kilojoule per mole. See part 1, complete figure 4.1. 2, draw the structure of compound A and name the compound B. Compound A is the product resulting from the reaction between bromoethane and aqueous sodium hydroxide. Whenever a halogenoalkane reacts with aqueous sodium hydroxide, this results in an electrophilic substitution reaction where the halogenoalkane is substituted by the hydroxyl group. So now you will have a dialcohol instead of the bromoalkane actually. Now as for naming product P, it has 2 carbon atoms with double bonds between them. There's a bromine atom, and since no other notations are seen here, that means all other bonds with the carbon atoms are those between carbon and hydrogen. This is a 2 carbon alkene with a bromine substituent that makes it bromoethene. Draw the structure of one repeat unit of polymer C in the box. Polymer C is produced by the reaction of bromoethene. Since there are no other reactants and the monomer of this reaction is a compound with carbon-carbon double bonds, that means it undergoes addition polymerization, where the double bond between 2 carbon atoms involved will open up to allow them to form new bonds with the adjacent monomer units and form the polymer. So that's your repeat unit. Reaction 5, compound B reacts with an excess of sodium hydroxide dissolved in ethanol. The products are hydrogen bromide, water, and unsaturated hydrocarbon D. Suggest the identity of D. Let's look at reaction 5. Okay, whenever a halogenoalkane reacts with sodium hydroxide in alcohol, it undergoes elimination reaction. So let's say you had bromoethane, right? If it reacted with sodium hydroxide in ethanol, that would have eliminated firstly the halogenoalkane over here, and also alongside the elimination of hydrogen atom on the adjacent carbon atom, and this would result in the formation of a double bond between the 2 carbon atoms which were involved in this. So as you can see, this results in the formation of a double bond. Now you already start with a double bond in reaction 5. During this elimination reaction, the bromine and the hydrogen atom on the adjacent carbon atom would be removed, and a new double bond will form between the 2 carbon atoms. So now there is going to be a triple bond between the 2 carbon atoms, and they are only going to be bonded to 2 other hydrogen atoms. So that's C2H2 being the identity of compound D. D, compound E, is the only isomer of 1,2-dibromoethane. So what's 1,2-dibromoethane? That's your structure over here. And compound E is its only isomer, where both of the bromine atoms are bonded to the same carbon atom. That's 1,1-dibromoethane. Identify the type of isomerism shown by E and 1,2-dibromoethane. E and 1,2-dibromoethane. Once again, since there is no double bond involved in this compound, that means it does not exhibit stereoisomerism. Therefore, it has to exhibit structural isomerism. And within structural isomerism, because this isomerism occurs due to the difference in position of the substituent, that is bromine atom, that means it is structural isomerism due to change in position. Name the homologous series that F belongs to. Here is the aldehyde group, that means it belongs to that homologous series. Complete table 4.1 to state what's observed when F reacts with reagents listed. Whenever an aldehyde or ketone reacts with 2,4-D and pH, it results in the formation of an orange precipitate. And aldehydes react with Tollens reagent to form a silver mirror due to the silver ions present in the solution. Alkaline aqueous, you will see the formation of a yellow precipitate, and that's because compound F has a terminal methyl group that's bonded to the aldehyde group. You would observe the same reaction if this terminal methyl group was bonded to a carbon that has a hydroxyl group, or if the terminal methyl group was bonded to a carbonyl carbon. Part E, compound F reacts with reagent G to form compound H. The infrared spectrum of H is shown in figure 4.3, and you're supposed to use the information to deduce the structure of X and explain your answer fully. This is an answer for 3 marks. Let's start with the fact that the absorptions that you see in this spectrum occurs due to all of the bonds in this particular compound. So that's the bonds in H that result in these observations, in these absorptions. And this broad peak, with this particular broad peak, is often an indication of the presence of carboxylic acid, where the OH bond over here causes this particular peak, right? And you would also confirm that by this range between 2500 to 3600 that occurs due to the carboxylic acid group. So we already know that H is gonna have 2 carbon atoms, and one of them is gonna be a part of the carboxylic acid group. So it is likely that this is the structure of H, but we need to make sure we cover all the angles and give enough reasons to score all 3 marks. Let's look at other absorptions, and I prefer to look at higher values in absorptions. The next highest value of absorption is due to this peak over here that's starting from 1600, right? Let's look at the table to find which bonds will result in this. Here we have the range. We obviously know there is no amide group since we don't have a nitrogen atom. This is also not going to be an ester because we have already determined the broad peak to be indicative of the presence of a carboxylic acid group. That means the peak that we are going to use in our answer would be caused due to the carbonyl carbon or the carboxyl functional group with the double bond between carbon and oxygen. Remember, these peaks occur due to the bonds, and this table tells you the potential functional groups that you could have in your compounds. This is confirmed when you see that this peak does lie between the range provided in the table. So now we know the compound H has a carbonyl carbon. It also has the oxygen hydrogen bond resulting from the carboxylic acid group. Lastly, we also need to use this information over here. H shows a molecular ion peak at 60. That means the molecular mass of H is equal to 60 units. Since we came to the conclusion that H is ethanoic acid, we can confirm our answer by finding out the MR of ethanoic acid. That's the sum of the mass of 2 carbon atoms with the mass of 4 hydrogen atoms and 2 oxygen atoms, and this is equal to 60. So now you have 3 factors to confirm your answer. Suggest the role of reagent G. Remember that aldehydes can be converted into alkanes by reduction, and they can be converted into carboxylic acid by oxidation. Since this is an oxidation reaction, that will make G an oxidizing agent. And this is it. We are done with this paper. Thank you for watching.